So for our last lecture, we looked at the expectation value or the expected average value for position, for the position operator, as well as the spread in position. Although we didn't look precisely at the n equals 1 state of the particle in a box, we looked at the n equals infinity, the sort of limiting case for the spread in the particle's position, which is a useful result in its own right and is a reasonable approximation for the n equals 1 state. Now let's move on to looking at momentum, expectation values for momentum, and again using the angle brackets to indicate expectation value or expected average. Also momentum squared, which is most useful for looking at what is the variance sigma squared p, or the standard deviation sigma p for this system. And you recall the momentum operator in quantum mechanics for 1D along the x-axis is minus I h bar d dx. So if we want to calculate the expectation value for a momentum, that will involve an integral. And you may recall that the wave function for the n equals 1, let's call it psi sub 1, is square root of 2 over a sine pi x over a, where little a here is the length of the box. So our average value of momentum is going to be equal to the integral over all space of psi star p psi d tau, which then, for the particulars of this case, we're talking about this psi 1 here, and we'll plug in our differential representation of the momentum operator. So that's going to give us, first of all, we're going to have 2 copies of psi 1, so we're going to get square root of 2 over a times square root of 2 over a, so that's going to give us a 2 over a that we put out front of our integral. And then in this case, again, like in the previous case, all space is actually confined to the, we had already decided the wave function only has some value between 0 and a, between x equals 0 and x equals a, and then it's 0 outside that range because the particle is just exists inside that box and has no probability density outside the box. So this apparent dilemma of what does all space mean is resolved in just integrating between 0 and a. And our wave function is going to be, of course, this sine pi x over a. And then our momentum operator is minus I h bar d dx sine pi x over a. And then our differential element there is dx. Okay, then let's see, the derivative of sine pi x over a is going to be pi over a cosine pi x over a, where I've used the chain rule to evaluate that integral. And, or sorry, not integral, but differentiation. Okay, now let's put our terms together. Let's see, so then we have this minus I h bar times pi over a cosine pi x over a. So we get, putting our terms together, we get 2 over a integral sine pi x over a, and then we have this, we're multiplying by a minus I h bar pi over a. Okay, so we're not subtracting that, we're just, it's a negative term there, minus I h bar pi over a times cosine pi x over a dx. And this again is from 0 to a. Now this is another one of these cases where we can look at this sort of graphically, in that we know what this function sine pi x over a looks like. So we're going to look or evaluate or look at this graphically, and so that first function is going to look a little bit like that. Clean that up a little bit. There, that looks a little bit more symmetric. Okay, and so that's the sine. The cosine is going to start off with a value of 1, and then at halfway through the box, so at pi over 2, it's going to go through 0, and then it's going to go positive. So it's going to look a little bit like that. So that's the cosine, and that's the sine over that range from x equals 0 to x equals a. So then if we look at the product of these two, it's going to look a little bit like this, right? At x equals 0, the sine function is 0, the cosine function is not, but the product is going to be 0. Then in the middle there, you have this positive lobe where they're both positive. Then in the middle, so in the sort of first half, yeah, they're going to be positive for a while there. Then in the middle of the box, the cosine function goes to 0, so then the product of those two goes to 0, and then the cosine function goes to negative, so the product of those two is going to go negative, and then it's going to go back towards 0 at the position x equals a. So it's going to look a little bit like this. And again, these are very symmetric functions. The first half of this is a mirror image of the last half. I know my drawing's not perfect, but we all know what sines and cosines look like. And so then the areas cancel and the integral goes to 0. Okay, and we could also look this up, solve this other ways, looking up integral tables or using computer algebra software, and we'll maybe get a chance to go back and do some of that later. But the end result then is that our average momentum in our box is 0. And if you think about it, momentum, it's like velocity in that it can be positive or it can be negative. If a particle is moving to the right, then in this coordinate system, then momentum would be positive. If the particle is moving to the left, then the momentum would be negative. And if we have a particle moving around inside a box where there's no external forces, it's going to be moving roughly half the time to the right, half the time to the left. And so the average velocity or the average momentum is going to be 0. Right? There's no, and that makes sense. The particle isn't really going anywhere for any extended period of time, and so there's no net velocity or momentum. The box isn't moving through space. The particle is confined in this one region, so the average velocity would be 0. Just like in the ideal gas case, if you think about a ideal gas where you have molecules bouncing around inside there, the average velocity along any one of those axes of the gas molecules is going to be 0. Now the RMS velocity, right, the root mean squared velocity, or the speed, is not 0. Right, the particles are moving around, but the average velocity is 0. Okay, so we've got a result, and we think about it, and it sort of makes sense based on analogies to similar systems. So far, so good. And of course, we can use mathematical methods, more rigorous methods, to evaluate that integral. Now let's move on to momentum squared. And you may recall that the operator momentum squared we can evaluate as minus I h bar d dx twice. And then we can just sort of group together the differential parts and the constant parts. And we get minus h bar squared d squared dx squared. So this is a second derivative type operator. And we go ahead and put that inside of and make our operator sandwich again. And the integral is going to be 2 over a, right? Those are the normalization constant parts. Integral from 0 to a sine pi x over a, and then we're going to have this minus times minus I h bar squared d squared dx squared sine pi x over a dx. And of course, let's go through and do the d squared dx squared on our sine pi x over a. That's going to be d dx times, or acting on, pi over a cosine pi x over a, and then acting our derivative again, we're going to get pi squared over a squared, and derivative of cosine is minus sine, so we have minus pi squared sine pi x over a. Okay, so then let's bring this constant and the, oh, I noticed a little error here. There's no I there, it's just minus h bar squared d squared dx squared. Okay, so we will put this minus h bar squared, the pi squared, and the a squared together. So that's for this part. We're going to plug that back into the integral. We're going to get h bar squared pi squared over a squared times 2 over a integral sine pi x over a sine pi x over a, so basically just that squared dx, and it's this integral over this range. And you may recognize this integral. We looked at this already, and this is the same integral that we get when we normalize our wave function. We know that our wave function is normalized, and so you know, we've done this integral before, and so this integral ends up being 1. All these terms, the 2 over a sine pi x integral sine pi x over a squared dx, that's going to integrate to 1, and so we get h bar squared pi squared over a squared. And this is just another example of the fact that, so it looks like this n equals 1 state is an eigenfunction of the momentum squared operator. In fact, also the n equals 2 state for the particle in a box and the n equals 3 state, they're all eigenfunctions of the momentum squared operator. They're not eigenfunctions of the momentum operator. So our psi1 is eigenfunction of momentum squared. And so it's interesting. You can be sometimes you can be an eigenfunction of momentum squared, even though sometimes you can have an eigenfunction of momentum squared, even though it's not an eigenfunction of momentum. And so we end up with this result, that the expectation value is equal to the eigenvalue. And we can see how that happens. It's because when you act then the operator on the wave function to the right, you get back that eigenvalue. It comes out of the integral. You get back also, because it's an eigenfunction, you get back the same function you started with. And you started with a normalized wave function. And so the integral goes to 1, and you get back the eigenvalue as your expectation value. So this is an example of what happens when you perhaps ignore or forget about momentarily the fact that there is this eigenvalue special case for evaluating expectation values. And if you forget and go ahead with the integral, but you still keep your eyes open, you'll recognize that you get an integral that you've seen before, and that it's the normalization integral, and that it goes to 1. And so you get the same result using the integral method as you would get using the special case eigenfunction eigenvalue method. So this is a nice little sort of pocket proof of our of the fact that the expectation value is the eigenvalue. Okay, then what is the spread, the variance, the standard deviation of the momentum operator? So we want to get sigma squared, and that is, for momentum, that's going to be the momentum squared operator, expectation value, minus the expectation value of the momentum operator, quantity squared. Okay, we know that in this case, but not in all cases, but often for momentum, if we're dealing with a stationary system that's not moving through space, the average momentum is going to end up being 0. So that's, but of course, position, the average position might not be 0. So don't always think, oh, this second. Don't overgeneralize and assume that always this subtractive term, this minus operator expectation value quantity squared, always goes to 0. It doesn't. It does in this case. It does in some other cases, but not always. And then this other one is h bar squared, pi squared over a squared. And of course, we can simplify a little bit in that our operator is let's see, we end up with h bar squared. Let's see, h bar is h over 2 pi. So we end up with h squared over 4a squared as our result. Let me just double check. Yes. Okay, so that is our uncertainty in terms of the variance. The sigma, that's our sigma squared for momentum. Sigma is just going to be the square root of that, so there's going to be h over 4, or sorry, h over 2a. Okay, then what else can we do? We can look at the Heisenberg uncertainty principle. And see if indeed our results are in agreement with this Heisenberg uncertainty principle for this system. So let's take a look at that. We get that, let's see, first of all, Heisenberg uncertainty principle, in terms of standard deviations for position momentum would be sigma x, sigma p. The product of those two is always going to be greater than or equal to h bar over 2. That's the standard deviation version of the Heisenberg uncertainty principle. And we can put our numbers in. Sigma x is a over square root of 12. That's a squared over 12 is sigma x squared, so they taking the square root of that. And that is for, of course, that is not, this is for n equals infinity, so this is going to be an upper bound for what sigma x is. So this is not exactly the most valid comparison of the system to the Heisenberg uncertainty principle, but let's go through with it anyway. So we get a over square root of 12, and then sigma p is h over 2a, as we see there. So the product is a over root 12 times h over 2a. The a's cancel, so that's nice. The product of the uncertainty principle hopefully shouldn't depend on the size of the box, right? That would be weird if it was valid for some sizes of box and not other sizes of box. So it's somewhat encouraging that a, the size of the box, is drops out. It's also encouraging that we get something like an h or an h bar here. So we can evaluate this. This is unfortunately not a simple, it's a fairly simple but not too simple expression. We can plug it into a calculator and actually see that after we simplify this, we get h over, let's see, square root of 2, that is square root of 4 times square root of 3, so that's going to be, so we have h over 4 roots of 3. And again, we've simplified a little bit, but that's we're comparing that to h bar over 2, where h bar is h over 2 pi. But we can plug the numbers in, and we see that in the one case, that let's see, the 4 pi is about 12.9 or something like that, whereas 4 roots of 3, or sorry, well, anyways, we can put the, I don't have the numbers in front of me, and I don't want to hold up the lecture, but you can, I'll leave that as an exercise for you. You can, it's fairly straightforward, just plug the numbers into a calculator, and you can see that we end up with that this is greater than h bar over 2. And so we've obeyed the Heisenberg uncertainty principle. We're not at, and this isn't the edge case. So it'll be interesting. Later we'll see a system where the product of the uncertainty in x and the uncertainty in momentum is exactly h bar over 2. And so that's the kind of the interesting limiting case, right? So the Heisenberg uncertainty principle says, for some systems, this product of the uncertainty in position and momentum is going to be larger than h bar over 2, but it's never going to be less than h bar over 2. That's what this is saying. And so this is certainly falls into the falls into that. All right, so that is enough for this lecture. And the next lecture will be looking at trying to apply this particle in a box model to the to some more interesting systems like pi conjugated electrons.